Yeah, for the pointer, right? Yeah. Works. Use this one here. Right. Yeah. Or should it wait? I'll change it to next slide. Wow, it should work. Okay, so just the arrow keys. Okay, now it's also working here. Perfect. Oh, yeah, it's just not the other way around. Just then rest on your ears. Just? Yeah, and then let's see if we put here. Okay. Perfect.
We begin on live. I'm François Dubois, and we chair the session this afternoon. And we have the pleasure to welcome Philippe Souffat, who will speak about highly parallel complex moving geometries on CPU and GPU using the partially saturated cell filter.
Yes, thanks for the nice introduction. Yeah, like what we want to do is with this partially saturated cells method is to fully resolve like complex moving geometries. Like here, this counter-rotating open rotor here. For example, this like wind turbines, the blades of the wind turbines. Exactly. But what we need for this is, first of all, like an efficient Lattice-Boltzmann method for this moving geometries. So we choose the partially saturated cells method, also called PSM. So I guess most of us know the classical LBM rule here. But like the difference to PSM method is not that big. So first of all, we have like in the first part of the equation here, we also have like the classical LBM, like just a fluid collision, but weighted by this weighting factor B, which is the solid volume friction field. I will go to that in a second. And the second part of the equation is a solid collision part, also weighted by this field. That is what the solid collision looks like. We don't really have to go into detail of this equation. It's like it just behaves like a no-slip boundary or like a moving no-slip boundary, more or less. Okay, if we look at the solid volume fraction field now, we have like an example geometry of an ellipse here. And inside the ellipse, the cells which are fully covered of the geometry are getting the fraction values 1. And cells which are fully outside of the geometry are getting the value 0. And there are some interface cells which get a value between 0 and 1. That means for cells which are outside of the geometry, like these here, the PSM update rule is really just the classical LBM rule because this part here cancels out. So it's just a fluid collision part. And for cells inside the geometry, it's only this solid collision part, so only something like a no-slip boundary. And only for the interface cells, we do a mix of both kernels, more or less, like both, yeah, fluid and solid. Why we do this is, first of all, we have only one kernel for LBM and boundary steps. That means that we can run over our whole LBM field and do only one update rule for the whole field, which is also very good in terms of consecutive memory accesses and therefore very suitable for GPU. The even bigger advantage is that this talk is about moving geometries. That means that this geometry will move one day and release like a solid cell to a fluid cell. And in other methods, this solid cell has no valid PDF values. That means you have to do some PDF reconstruction, which is expensive and can lead to instabilities and all this stuff. But with PSM, this is not the case. And this is also very, very suitable for GPU. Also worth mentioning is maybe that we included this partially saturated cells method in our code generation framework, LBMPy, which is capable of generating code for all different collision operators like SRT, TRT, cumulants, central moments, all this stuff. And it's also capable of using different streaming operators like push-pull, AA or isotwist or all this stuff. And it can even generate code for CPU as well as AMD and NVIDIA GPUs, which is the most important part. So what we need next for our goal for efficient LBM simulations for fully resolved complex geometries is like an efficient rotation of these complex geometries. So we have an example of this geometries. This is here the counter-rotating rotor. And you can see here already this geometry comes as an STL object file, and this has like 1 million or more vertices and faces. So this is like a very complex geometry. And what you could do now is like, if we want some rotation here of these blades, we could like rotate the vertices and cells in every type step and then map it back to a LBM grid. But this is super expensive. This is not what you want to do, because then you have to do a voxelization in every time step. So this is just too expensive. So what we instead do is like introducing a geometry field, and we map this geometry mesh, like this mesh here. We map it onto a field, which is more or less the same like an LBM field, but it's like a super sampled field. So you can capture all the shapes of the geometry by just increasing the super sampling. And it's only pre-processed once, so it means like we only do one voxelization at the start of the simulation, like a pre-processing step, and then it stays constant. So what we want to have is the fraction field for the PSM. That means that we have to interpolate from the geometry field to the fraction field. It means we have some lookup, like some mapping from the fraction field to the geometry field, and some simple interpolation. And this you can do in every time step, and it's very efficient, which we see soon. The question is now how we handle like rotation or movement. The geometry field does not only store like the shape of the geometry, but also like the rotation or translation information. That means for this example, it stores some sort of like rotation angle. And while mapping from the geometry field to the fraction field, we just include the rotation angle here in the interpolation. And therefore, we get like a new fraction field from the geometry field without really rotating a field, but it's just like integrated into the interpolation, the rotation. And this is also very, very cheap again. So the next step is the validation of the PSM method. And there's like this very famous test case of the settling sphere from 10K et al, which just settling down from gravity. And they tested it for 4 different Reynolds numbers. And the reference values are these crosses here, and like our results are the lines, and we can just see that we're in very good agreement with the reference data for our PSM method, which is quite nice. And lastly, we want to look at some performance benchmarking. So we tested like 2 scenarios. One scenario is like the one rotor of the counter-rotating open rotor geometry, and the second scenario is the full geometry of the counter-rotating open rotor. So that means there's a bit like the worst case scenario here, because there are a lot of boundary sites rotating over the whole domain, and this is only a rotation in a very small part of the domain. First of all, we tested the CPU node level performance. We tested like PSM versus LBM. And we can see that like the PSM does not really introduce any performance penalty at all. So it's more or less the same performance as LBM. And we also see that we are like kind of close to the memory roofline here on the CPU for LBM and PSM. Of course, like the scenario A is always a bit slower than scenario B, because there are more boundary sets to handle. And if we look at the 2 plots here, this is the PSM plus the rotation, so the interpolation I introduced before. And we also see that the interpolation is very fast, so there's no big overhead of doing this interpolation. Then next we look at the GPU performance, and we see more or less the same results. We're also like PSM and LBM is both more or less same speed, same. We plot here the mega lattice updates per second. That means like how much LBM cells you can update per second. You can update per second, more or less. And we see that we are again very close to the roofline of this in this case an NVIDIA A100 GPU. We can even see that the PSM method for scenario A is a bit faster than the LBM here, mostly because of the consecutive memory access we can do. And we also see that again the interpolation or rotation, as they call it here, does not really introduce a big overhead. And this time it's like 10% on GPU. It's a bit bigger than on CPU, but not too much. We tested here. This means like different super sampling strategies. We also did some strong scaling of this counter-rotating open rotor simulation. First with a small problem size of 200 million cells here. And we scaled it up to the power of 12, to the power of 13 cores. But we see that at this point, the problem size is a bit too small for the number of cores, so we could get some performance drop. Therefore, we tried another problem size, like a bigger one, so 3 billion cells, 3 billion LBM cells. And there we could easily scale up like with very good scaling efficiency up to the power of 15, so 32,000 CPU cores on this LumiC HPC cluster. We can even reach like a refinement mesh size of 0.3 millimeter on the geometry. And we also did the same performance strong scaling on Joules Booster, like the GPU cluster in Jülich. And there we were able to scale up to 1,000 GPUs for this big problem size of 4 billion LBM cells. There we can see some visualization, which is not working, unfortunately. But yeah, there's where we are right now. This is like this counter-rotating open rotor with like the Q criterion around. We simulated this on like 36 GPUs, A100 GPUs with like of course the cumulative method to make it stable. But of course, like as you can see here already, the Reynolds number is still quite low. So we did not try to push the Reynolds number higher yet. This is like the next step. That means what we really want to have is like Reynolds numbers of 1 million or more for these two test cases here. That means we want to have like heavy exploitation of mesh refinement. It could be like kind of likely that we also need some wall modeling for the PSM method. And lastly, we want to do some more validation cases for this PSM for high Reynolds numbers at first, because I guess there's no literature for that yet. So we want to test like this terminal flow around a sphere test case. And also we are searching for a validation test case for a complex moving geometry, but it's hard to find any literature there. So if you have any ideas, please tell me. And that's it for my talk. Thank you for your attention. And if you have questions.
So you may have said it, but what exactly? So you have the partially saturated cells, so you split up your collision operator those bits. So at boundary cells, you have like a link bounce back. Is that right? When the full filling fraction is 1, or and then when you have partial filling fraction, you have some partial bounce back of a partial fraction, normal collision for the rest.
I guess you could say it like that. Like of course, you do full some sort of no slip here, like this the real solid collision term, and this is usually used for particles. So this is very famous in particles, particle fluid coupling. And yeah, if you're at this interface cells, then you do like a mix of fluid and solid collision, and if you're like there, you do only solid collision.
Yes.
Did you test the order of this boundary condition?
I think yeah, there's paper for it, but I think I forgot the order. Sorry, but like it's famous.
Show it you need maybe from the position of your boundary.
Yeah.
Wondering, like, if you do a rotating geometry, you can also do some other method and just use sliding mesh.
Yeah, of course, there's some other methods as well, but like we try out because this is something new, more or less. Yeah. Of course, there's also actuator line or like immersed boundary or all this other stuff you can do. There you need some like DEM, right? It's not implemented. Yeah. Yeah, in this case, it's only like the wall here, right? And because you have like there's of course no interaction because there's only one sphere dropping down, right? Or what do you mean? No, it's not, because there's like the idea is that we only have like one geometry which is moving. Yeah. So it's not really about particles anymore. Yeah.
Is that a question? Yes. So when you do that recoloring of the LBM sites,
Yeah.
they really need to use the refined lattice representing the geometry that you create in the pre-processing, or can you use STL data, for example, directly?
Like if you need like this field here.
Yeah. Can you do you need to voxelize it in the pre-processing, or can you use STL straight away?
Yeah, if you want to make this rotate, right, then you have to like make all the vertices and faces rotate, like the position. This is can be expensive, but even more expensive is the mapping then to the LBM field, because of course you need the information in the LBM field, right? The information of the geometry.
Not always interpolate after each like rotation by
Yeah, but that's much cheaper than like a voxelization. Like much cheaper. Like a voxelization here needs multiple seconds, and if you want to do this in every type step, that's super expensive. Kills all your performance.
Yes.
So simple that we just count the points then is that if you just count the points of the super sample in the figure itself.
Yeah, that's like, yeah.
So that principle, this is the thing that you actually have like only a few categories of intermediate steps, like depending on your super sample, like
Yeah.
only 100 or 128 or 50.
Yeah.
How many cells in one cell?
I'm usually working with a supersampling of 2 or 3. That means you have like a supersampling of 1 means that you have 8 cells per cell. And then 2 means 2 to the power of 2 to the power of 3.
Yeah.
And this, so it's, yeah. So you can really increase the stepping. Yeah.
The last question? So if not, we thank you again. Now to the second presentation.
Is it yours?
Yeah. but you can use it if you want.
Thank you. Mhm.
So the second presentation. The micro. Second presentation is proposed by Google. I'm sorry for the pronunciation. Quantum algorithm for solution, particularly to mechanics. It's to you.
Yes, thank you for being here. So first of all, I'm not talking about lattice Boltzmann. I'll be talking about something much more interesting, which is quantum algorithms for SPH. No.
It should work now, I think.
Okay. So first of all, I am part of a research team called Quebec, Quantum Enhanced Verified Exascale Computing. It is a project in Excalibur. This is a program that focuses on developing exascale codes, exascale software and hardware for scientific computing. And fluid simulations is one of the things that we focus on. And these are the grants that we were funded by. The outline of my talk. So first, I will talk about the aim of our project. Then I will compare mesh and particle-based CFD methods. Then I focus on like SPH in particular. And I introduce a quantum algorithm for SPH by solving the advection and diffusion equations. Then I discuss the future work that we want to do before I conclude. So first off, the aim is to develop quantum algorithms for SPH. We want to identify the bottlenecks in the SPH method and see if quantum algorithms can fix some of those issues there. And we do so by showing a proof of concept, by solving two very commonly encountered PDEs, the advection and diffusion equations. And this is the paper that we published. So first off, in mesh-based methods, like in the figure on the left, where we model an airplane wing, we can use a mesh-based method, which involves drawing a mesh around the region of interest and then calculating the properties of interest at all the different nodes at each time step. So a lot of commercial software like Console and Cadence, they use mesh-based methods like finite volume methods to do the calculation. The problem is when there are lots of violently deforming fluids, like waves crashing onto the shore, this becomes much more difficult to draw the mesh. And the problem is the mesh generation process is usually the most computationally expensive process of the whole numerical algorithm. So one alternative is to look at particle-based methods. Here we have no mesh. Instead, we have lots of particles that carry the fluid properties, and they all freely move around our computational area. So for example, in this example, we have two planets colliding with each other, and it uses SPH. So SPH was developed in 1977. It was first used for astrophysics problems. And in the following decades, people gradually refined it and adapted it to use in engineering problems. And today it's commonly used in civil engineering and mechanical engineering. So there are 3 basic steps in SPH. First, we do a domain discretization. So we have a continuous fluid, and we discretize it by taking a set of randomly distributed particles, like shown in that figure. Second, we do a field function approximation. So we approximate the function using an integral representation. And then finally, we do a particle approximation. So we convert that integral into a finite summation. So what does it mean in practice? It means that if we have a continuous fluid, we divide the domain into randomly distributed particles. Each particle carries the fluid properties, like the density, temperature, velocity, and so on. And we update these properties at each time step by following the conservation laws of mass, momentum, and energy. So for example, if we want to approximate some function, f, the r is the particle position, we can approximate f by taking the weighted sum of all the contributing particles inside the area of interest. When I say weighted function, it means we use a weighting kernel or a smoothing kernel, which we denote as W. And this weighting kernel is closely related to the convergence and the stability of the SPH algorithm. And so as a result, it must have some certain properties. So it must be symmetric and well-behaved. It must be smooth and monotonically decreasing, normalized, and have a compact support area. And a Gaussian is a commonly used example of a kernel. Now, the problem is, when we use SPH, we need to use a lot of SPH particles to simulate problems of practical interest. Like in the astrophysics example I showed earlier, that figure required about 100 million SPH particles to calculate. So if you have that many particles, there are ways to deal with it. Like you can use parallelization strategies like GPU or HPC. But one other option, which isn't as explored as the other possibilities, is quantum computing. And this is the motivation behind our work. So in our paper, we develop a quantum algorithm for SPH. It is a proof of concept. So we take the simplest possible system. Specifically, we take a system on a line. This one-dimensional system contains SPH particles positioned along the line, and they are equidistant. They don't move. And we take the system and we use it to solve the one-dimensional advection equation shown here. So we have the advection quantity U and advection speed C. And what we expect is, if we start with a state like a graph centered at 0, so the blue graph here, the advection of the system means that the graph will just shift horizontally to get the orange graph. And as you can see, the graph doesn't grow any wider or shorter, so there is no diffusion involved. So we have the PDE. Next, we write this into SPH formalism. This isn't anything new. You can find it in textbooks and reviews. Now, the thing that we do is we take the summation term and we want to encode this into a quantum computer. And to do so, we need to do some manipulation. So we take the summation and we rewrite it as an inner product. That means we take one part, specifically the advection quantities, and write that as one vector, and we take the kernel and we write it as another vector. And as a result, we turn the summation into an inner product. And that symbolism is an inner product. So now we have this equation for quantum SPH. We want to put this into a quantum computer. There are some quantum encoding procedures that we can use. One of them is the quantum amplitude encoding. This encodes the floating point numbers or neoclassical information into the amplitudes of a quantum state. And once we put this information into the classical computer, we can do the calculations. So we do the inner product, yes. And once we calculate that, we pass it back into the classical computer using a quantum readout procedure. And then we repeat the whole process for the next time step. And this is, yes, I saw that. So the initial state, we have a graph that's centered at 0, and we see that it moves to the right. Now, the quantum algorithm gives us a very smooth curve like that. The blue and the orange graph is the result of the quantum algorithm, but using different kernels. And they're basically superimposed, so you can't really see them that clearly. And for comparison, I also calculated the classical solution using Lax-Wendroff. That's shown as the dashed green line. Again, it's superimposed with the other graphs. And the exact solution is the red dotted line. So you can see that the quantum solution, classical solution, and exact solution are in really good agreement. Now we can do the exact same thing, but with the diffusion equation. So now we have a second order PDE. We rewrite this into SPH formalism, then we write that into the quantum SPH. Now we have the solutions here. The black graph, the tallest graph, is our initial state. As time goes on, the graph grows shorter and wider. The graphs have different colors, which represent the different time steps. And the graphs for the solid line are from the quantum algorithm. The dashed lines are the classical solutions, and you can see that they are all in good agreement. So to summarize, we take a very simple system, a proof of concept, to show how a quantum algorithm for SPH could work. Now, because we have a one-dimensional system, we need to be able to extend this to 2- or 3-dimensional systems to make it more useful to solve engineering problems, astrophysics problems, and other scientific applications in general. Now, we have taken a lot of simplifications. So these SPH particles are all sitting on a line. They can't move. In SPH, they need to be able to move because that is the inherent strength of the method. And that means that we would need another quantum register to store the information. So store the particle position information. So that will be another degree of freedom. Another issue is the time stepping. So you can see that at each time step, we transfer classical information to the quantum computer. We do a calculation, we pass it back to the classical computer, and we do this whole thing again for another time step. Now that needs to be much more efficient, obviously, because quantum encoding is a very computationally expensive process in general. Amplitude encoding in particular is expensive, and it is an active area of research in the quantum community. And this is an important thing to investigate because if the encoding and readout procedures take more time to implement than to just do the whole thing on the classical computer, there is no point in having a quantum algorithm. There's also a neighbor search, which is required for calculating the kernel. There are existing techniques like neighbor listing, verlet listing that are quite fast, and we can also use GPU and other parallelization strategies. So we would have to adapt that to a quantum framework. Another option is to do a quantum search algorithm like Grover search, which has been proven to be much faster than classical search algorithms. So in conclusion, I showed a proof of concept for a quantum algorithm to do SPH. I used it to solve the advection and diffusion equations. And in future work, we need to be able to move these SPH particles around so that it looks more like SPH and not like a mesh-based method. And we need to figure out how to do the time stepping, make it much more efficient. And yes, quantum encoding, which is really important in quantum computing in general, especially in quantum machine learning and fluid simulations, material sciences, and scientific computing in general. So I'm open for questions. These are some references you might like to look at if you're interested in quantum or SPH. The top two are papers that we did recently. One of them's the SPH, the other one's a review on quantum computing in general. Yes?
By curiosity, have you tested your algorithm under noise you would expect on a real machine?
So what we did was we simulated this whole thing classically. So even the quantum computing parts. So in this figure here, we calculated the inner product using Python. It was just a brute force inner product. We didn't actually use any quantum algorithm to do that inner product. Because this is really just a proof of concept. We're not concerned about like quantum benchmarking or verification or even noise, because we need to be able to before we run, basically.
Yes. So thank you very much for this introduction and very cool stuff. And this Grover search, could you just briefly outline how it can perform so well?
How long do we have?
I don't know. I think it's 1 or 2 minutes left. Just in 2 sentences or 3, what's the advantage that you gain on the quantum?
Well, in theory, you gain a quadratic advantage. Grover search uses amplitude amplification. So if you have an equal superposition of many, many states, this amplitude amplification can pick out what your state of interest is, and it will give you the answer in quadratic time. I mean, I would need a lot longer to talk about this.
What questions or remarks? Yes,
I mean, so do you think, because SPH is a pairwise method, do you think this would be beneficial with the quantum gates, which also involve 2 qubits?
We're actually working on that. So I'm not really sure how much I can tell you about this. Yeah, sorry.
Was questions?
So it's not thanks to, thank you again.
That. Thank you.
Ben.
After 10 minutes, I will show some.
Yeah. Okay. Do I have a stick?
There is. Does this work?
Ah, yeah, I got it. I found it. Yeah, I
Okay. We have the pleasure now, the last speaker of this session is Ben Picard with leveraging symmetry for Einstein efficiency, a new approach to tailor grid vortex calculations. Ben,
Thank you very much for the kind introduction. In this case, you pronounced my last name perfectly. So thank you very much. My name is Ben. I am a master's student of the University of Applied Science Bonn-Rhein-Sieg. And I'm going to talk about leveraging symmetries for enhanced efficiency. So in general, what we're going to do is we are implementing a symmetric boundary condition to just take the friction of a fraction of a full symmetrical flow to gain some advantages. For the one hand, we can just pick out, oh no, I can use the stick, this little part, pick it out and just also cut down and take the same friction of the grid. So in theory, we should get the same results with a way lower and smaller resolution. So we get a huge time advantage, which could be very efficient for machine learning, as you may have noticed yesterday, Mario Bedrunker, who's in my group, who's doing research on machine learning. And on the other hand, we could use the friction of the full domain and put the same big grid inside this domain, so we get a huge precision advantage. So I'm going to show you a little bit how the symmetry boundary condition is going to work and which advantages we are going to get. So first off, to implement and to test the symmetric boundary conditions, we need a symmetrical flow. In this case, we used the Taylor-Green vortex. How does it work? Oh, yeah. Yeah, now it's working. So a quick reminder, the Taylor-Green vortex is a 2- or 3-dimensional velocity and pressure field. We initialize the pressure and the velocity we got in 2 dimensions for vortexes who are rotating clockwise and counterclockwise, and as well in 3 dimensions we got 8 big vortexes. We initialize the pressure and the velocity, and what we're going to do is we need first to analyze the symmetry to find out how can we use the symmetry to lower the full domain. So we're just going to take, as you may have seen, this little part. As an example, we are going to illustrate the symmetry of the Taylor-Green vortex in 2 dimensions. We're going to take this part, this quarter of a vortex, and we can rotate it in 90-degree steps and create the first vortex. After that, we can mirror it on the first axis and the second axis. So as we see, we just need this little part of the initialization to have a representation of the full domain. So the periodic Taylor-Green vortex, which is periodic in 2 pi intervals, can be reduced by 1/4 in every dimension. So as we have seen, we just need 1/16 of the periodic full domain we standardly simulate. And in 3 dimensions, it's even 1/4 to the power 3, so 1/64 of the full domain. So as we have seen the symmetry, we are now going to take a look at the symmetry boundary condition, starting with the periodic boundary condition. You probably know about this boundary condition, but you will see why I give you a little refresh. So we got our full domain of the Taylor-Green vortex. We're going to discretize it, this example in 16 times 16 nodes. And due to periodicity, it's going to look like this. It is a repeating flow field. And if we got an outlet right here, we can found it as an inlet right on the opposite side. And this is how the periodic boundary condition is standardly working. And it is, and that's important, standardly implemented in the Lattice-Boltzmann code I'm using in the university where I do the research. So right now, we're just going to take this little part, and the surroundings are going to look like this. So if we find an outlet right here, we are going to find it as an inlet right over here. It is shifted and rotated. So the problem is this node is non-existent. So what can we do? In every time step, we are going to put this population, who will realistically appear right here, on the opposite side where the node is existing. So the population right here in every time step will flow on the opposite side and will end up right here. This is how the symmetry boundary condition will work. At the end of the day, we are going to take the population right here, rotate it and shift it to this node to attack or to flow on these 3 grid points. So in a mathematical function, you can see it right here. We are going to adjust the distribution function f on a node, which is represented by xa and xb, to a time step t, and we got I and j, which represents the index of the vector of the stencil or the distribution function, which points in the same direction. So as we can see right here, we got our shift step where we are going to shift the population from here on this node, and on top of that, we're going to rotate this rotation, this population by 90 degrees down here. This is how the symmetric boundary condition is going to work. We need to find out which population will end up where and which transformation or rotation is going to be needed, so we can have the correct behavior. So we are not going to do it in 2 dimensions. We are going to do it in 3 dimensions. So as we can see, and as you have seen on the title, this is what we are going to simulate. Not the full Telegreen vortex, but just this little part, which is 1/4 in every dimension. So we are going to start with the setup. We used mainly the BGK collision operator and as well the KBC. We're going to see later on why. We simulated the Taylor-Green vortex as a full domain and as a reduced domain. We calculated the kinetic energy. And after that, we calculated the dissipation, which is our reference for comparing with the literature. So to clarify, our full Taylor-Green vortex, we're going to calculate it with a resolution NO, which stands for resolution of the original Taylor-Green vortex. After that, in the first case, we are simulating the reduced Taylor-Green vortex with an identical resolution, which means we divide the resolution of the original Taylor-Green vortex by 64, so we should get the identical resolutions. And on top of that, we're going to simulate an identical grid. So we just take the fraction of the full Taylor-Green vortex and we put the same grid of the original Taylor-Green vortex in the reduced one. So let's come to the results. I did some simulation with a Reynolds number of 1600 and the BGK collision operator. On the left hand, we can see with an identical resolution. So my original Taylor-Green vortex got a resolution of 128 to the power of 3 and the reduced of 32 to the power of 3. Got the identical results on the dissipation over the time graph. We are plotting as well the reference supported by Fehn et al. So as we can see, and what was the first idea, we got the same results with a way lower fraction of the full Taylor-Green vortex. And on the right hand, yeah, we can see we got an identical grid. So we got an original telegreen vortex with a resolution of 128 to the power of 3, and as well the reduced, which will end up in a resolution of 512 to the power of 3. So as we can see, the results of the reduced telegreen vortex, which is marked with a cross, is way better than the original due to the higher resolution, which is obvious. So we are going to take a more detailed look on both cases. First off, we are going to look at the maximal hardware usage. So I simulated at a NVIDIA A100 with 80 gigabytes VRAM, and the maximum resolution I could calculate was about 300 to the power of 3. So I calculated the telegreen vortex with a Reynolds number of 10,000, the original telegreen vortex. And as we can see, and that's also the reason why we used KBC as well, the BGK operator isn't stable at these high Reynolds numbers with this, I would say, low resolution. Well, the KBC operator is stable, but we don't match the dissipation pretty well. But on the right-hand side, as we can see, we did the same simulation with a resolution of 300 to the power of 3 with the reduced telegreen vortex, which will end up in a resolution of 1,200 to the power of 3. And we see we match the dissipation rate pretty well. So hardware limitations are lifted to a new level, enabling the creation of previously unachievable data. Now we're going to take a look at the efficiency when we work with the identical resolution. So we did simulations at a Reynolds number of 1,600 with different resolutions. Yeah, these resolutions are the resolution of the original telegreen vortex. So we did the simulations also with the reduced telegreen vortex, with who got a 4 to the power of 3 resolution due to the reduction. So we calculated the identical full domain. 5 minutes? Okay. As we can see, this is the fraction of the time for the full simulation from the reduced telegreen vortex divided by the time needed for the simulation from the original telegreen vortex. In low resolution numbers, like here 80 to the power of 3, we got a time reduction of like 45%. Yeah, we need about 55% of the time of the original telegreen vortex. But if we go further in the resolution, my time is going, or the frictional time is going lower and lower and lower. And at the end, right here, which is the maximum 300 to the power of 3, we could reduce the time over 69%. So at the end of the day, the higher the resolution, the higher the efficiency. So let's come to a conclusion. This is the telegreen vortex with Reynolds number 1,600 after approximately 10 seconds. First off, we got the identical resolution. So right here, we got a resolution of 100 to the 128 to the power of 3. And right here, 32 to the power of 3. And as we can see, or hopefully you can see it, this is exactly the same behavior. And as well, we simulated the whole flow with an identical grid. So this is the identical grid, the reduced telegreen vortex with a resolution of 128 to the power of 3. And as you can see, this one is way more precise than the one on top. So thanks for your attention. You can ask me any questions if you want. And yeah, that's it for me.
Thank you.
Not so many, please.
Yes, I did not fully get why you like get more efficiency with the algorithm when you increase the resolution.
Yeah, okay. So the problem is the boundary condition needs time. So when the lower my resolution is, so my surface grid points are like 6 times my resolution to the power of 2. But my volume, my grid volume is the resolution to the power of 3. So the friction of that is always going lower, lower, lower. So the surface is taking a smaller part in relation to the whole volume. That's the reason I think why it is later on more efficient than before. No problem. I hope so. So I got like some examples. Wait. This is way faster. For example, it should be possible for the double periodic shear layer. It is not that huge gain of efficiency, but as you can see, he is like on this line symmetric. So this should work here on the double periodic shear layer. And as well, what we're doing right now in our work group, we are doing some research on, I would call it acoustic shock wave, where we got a pressure point or a pressure circle in a field, which is moving. So, for example, we could probably divide this also by half in every dimension and just simulate this quarter of the whole flow. This is probably 2 examples I found pretty fast. So everywhere where you got some symmetry, even though it is a high symmetric flow like the Taylor-Green vortex or a low symmetric flow, I would call it low symmetric flow like the double periodic shear layer, it should be possible to use these symmetry boundary conditions. Yeah. Yeah.
For example, if you take a cylinder to a certain Reynolds number, the solution with the soft, you compute this stable solution.
Yeah.
So this is a great danger of your method.
And this is funny. This is funny because this is going to be my next project where I want to do some research. Because for example, when we calculate with different data types, one big disadvantage is that we lose symmetry in symmetrical flows. So with a symmetric boundary condition, we always, like you already said, we always got the symmetry in our flow, not depending on a data type or some errors to lose symmetry.
Thank you again. And thanks.
Thank you very much. Merci beaucoup.
You're welcome.
Thank you.
So.
Ja, wie das am Anfang bei mir aus, das war eine Folge.